Okay, so welcome to class 27. So yesterday we were actually looking at we were trying to in the previous class, not yesterday. So whenever you saw that lecture, we were actually trying to look at some of the more popular structures. We went from diamond cubic to lessened the symmetry a bit more, went to zinc blend, and then said the sister compound of the sister structure of zinc blend is what is called a Woodside structure, and Woodside is actually a very useful structure in electronics, right, because you have these the so called HEMTs or high electron mobility transistors, which are made by putting two Woodside structures on the top of each other and very nicely growing them on the top of each other. That itself is a big skill. Which actually we do. So there are people in my department in the Indian Institute of Science who are very good at growing these heterostructures, right. So and then making these HEMTs, high electron mobility transistors, right. So if you get a chance, you may want to take a look at our website and then see what is the research that is going on there in that area. But the fundamental material sciences, I put materials of two different polarizations on the top of each other, both of them Woodside, both of them 6-3 symmetry, right, and the 6-fold axis is the axis of spontaneous polarization, and this difference in spontaneous polarization should be compensated by some free charges, okay, and those free charges are in this case free electrons, and so you have a free electron gas, okay. So that's where we stopped. So we will park our discussion on Woodsides there. I also told you that in the assignment of this week you will be calculating the polarization of one of the Woodside structures that will give you probably only aluminum nitride, and you will use similar ideas as what we have done to calculate the spontaneous polarization of barium titanate in this class, okay. But it's a different structure altogether, right. So you can use similar ideas. We'll give you hints and other things so that you can get to the correct answers. Okay, all right. So with that, so let us before starting what are called symmetry property correlations or structure property correlations, let us actually look at a couple of other structures which are also sort of very basic structures. One is and these are because so we have to do justice to metallurgists also, right. So these are metals, typical structures encountered in metals, right. And so one is an FCC platinum or gold or whatever, right. So all these bunch of materials, and the other one is what is called an HCP, or HCP is not really a crystal system or crystal structure. These are what are called cubic close packed structures, right. So these are the closest packed cubic materials that can ever be there, right. So I'm not going into many details, and they all tend to be in face centered cubic, right. So the most popular examples of the crystal structure is face centered cubic. Then we have what are called HCP structures, HCP or hexagonal cubic hexagonal close packing. So where if I assume that all the atoms are touching each other, right. So and these are metallic atoms, so metallic bonds are just modeled as if the atoms are just touching each other. These are solid spheres, hard spheres which are just touching each other. That's my bond, okay. So then in a CCP or an HCP structure, I have the maximum packing, which means the number of voids. This is a void, for example, right. So all the things that are in this red color are voids, right. So this one, this is a void, this is a void, right. So I am going to minimize the number of voids, right. So the void fraction is going to be the maximum amount of void fraction I can have is about 26%, right. So 26% there is nothing, the other 74% is filled with atoms, right. So other 74% is filled with atoms. So these are standardly studied in metallurgy, because most metals take try to pack themselves, so metallic bonding is such that you can just model it with hard spheres, and they pack themselves in such close packing structures, right. Now CCP, so for example platinum, gold, all these things take a CCP, are cubic close packed structures, and the crystal structure, right. So now I have to give the centering and I have to give the symmetry, right. So it's a cubic structure that I know, but this is FCC typically, right. So face centered cubic. Okay, so that's the crystal structure. Not all FCC need to be CCP. Okay, CCP is cubic close packed, right. So but if I have a cubic close packed structures, typically they tend to all take the FCC structures, especially the metals. Okay. Now, what is, if it is FCC, I ask you the question, what is the space group? Space group is again, so my holohedral point group in in face centered cubic materials, that is M3 bar M. So I have FM3 bar M, so these are really high symmetric structures, and so I can actually visualize it. So here I have gold, right. So so I have fourfold axis about A, B and C, nothing really changes when I switch from A to B to B to C, right. So that's my that's my face centered cubic, right. That's my unit cell, and in my unit cell you can see that all the face centers are sort of occupied, and all the corners are occupied by gold atoms. So it's a very simple rendition. I am saving the simplest structures to the end, sort of, right. Now if I actually look at it along the not the boundary, but rather if I just look at it, I am doing this for completion, right. So this, I guess, will not be that difficult for you to understand. So the projection vector is going to be 1 again minus 1 0, just like we did for zinc blende, and the upward vector is 1 1 1. If I apply, then I see that so okay, so these are all the 1 1 1 planes. These are supposed to be close packed planes. So you can imagine that these all atoms are sort of touching each other. If I space fill it, yeah, so something like this, right. So these all atoms are touching each other, right. So these are hard spheres that are touching each other. Okay, but you can see that so this is this so if I denote so here sorry, rather than doing that, let me (1 minus 1 0) and 1 1 1. Okay, all right. So now I can actually see that maybe I cannot write here, but I'll try to point, right. So if this is the A stacking, right, if this is the A stacking, right, so I'll point here, then this is the B stacking, this is the C stacking, everything is sliding on the top of each other by 1/3 one of the lattice parameters, and then the A comes back, right. So the fourth stacking is again the A stacking. So I can so this is this one and this atom, right. So these two are right on the top of each other, right. So this atom and this atom. Okay, so just bear with me. Okay, so this crossed atom and the atom that I am pointing, they are right on the top of each other. So those are the same stacking. Okay, so so what I have here, if I'm viewing it along the 1 1 1 axis, right. So if I view these things along the 1 1 1 axis, I am going to visualize the structure as an A B C stacking. All the A is a plane made of it's a 1 1 1 plane made of all gold atoms, which are all closely packed with respect to each other. B is again another 1 1 1 plane of gold atoms, which are all closely packed with respect to each other, but they are slid by 1/3 compared to A, right, in this direction, that is the close packed 1/3 1 1 0 direction. Okay, and C is again 1/3 slid, and when you come back to A again, the unit cell finishes, right. So that's when the repetition starts to happen, right. So ABC. This is exactly like the zinc blende structure that we have seen. The stacking is ABC sort of stacking, right. Now zinc blende also had a sister compound, sister what did we call it, sister structure, we call it the Woodside structures, right. So typically thermodynamically they both are equally metastable or equally stable in many of the compounds, right. Well, not in gallium nitride. For example, in gallium nitride, Woodside wins, right. If you do the thermodynamic stability calculations, right. So which one is energetically more stable than the other? Okay, but in cases like cadmium sulfide, cadmium telluride, and all these materials, right. So Woodsides and zinc blends can coexist together, right. So similarly, the sister, so when I talk about a CCP, I should also talk about its corresponding hexagonal sister, and the hexagonal sister is the packing is close packing. If it is close packing, I call it HCP, hexagonal close packed, right. So that is something like titanium, right. Now in a hexagon I cannot, so all the only sorry, titanium or zirconium and all these sort of metals that crystallize in a hexagonal structure. In a hexagon, right, so the only cell I can have is a primitive cell, right. So I don't have a hexagon centered hexagon, right. So I lose the 6-fold symmetry if I center any hexagon. This we have seen earlier, right. And you will see that all these materials have a 6-3 sort of symmetry, right. So 6-3 axis, just like we had for woodsides, okay. And so you have slightly more symmetry than woodside, because so all the stacks are not aluminum nitride, they are all symmetric units, right. So just one atom was so the asymmetric unit is so to very loosely use the unit that is repeating is not aluminum and nitrogen, right. It is not a dumbbell, it is not an asymmetric dumbbell, it is a symmetric unit, right. So you will have more symmetry than what a woodside has, right. And in fact you can check here that the symmetry is going to be P63 by mmc, or in other words the underlying point group is 6 by mmc, sorry mm, right. Now 6 by mm is it is a centrosymmetric point group. So there is no question of these hexagonal metals being piezoelectric or something like that, right. So they are all centrosymmetric. Okay, that is good. So now can we identify where is the so if we look at what 6-3 means, so if I start with this atom, right, so I have to if I start with this atom, so and then I have a 6-fold axis which is somewhere centered here, then I have to rotate it by 180 and I have to come here, right. So so if I start with this atom, and then this is my 6-fold axis of symmetry, I rotate it and I put it here, and then so the third atom again goes here. So this is going to be my hexagonal unit cell C, right, and so I am going to create these sort of units everywhere, right. So with respect to the unit cell, and that becomes a structure like this, like you have seen, right. So along the C axis that you can see that this is the A stacking, this is the B stacking, this is A stacking, this is B stacking, and so on and so forth, right. So you exactly get what you have studied all this while. So this will have a series of atoms that can be called A stacking. This will have a series of atoms that can be called the B stacking. They are displaced by 1/3 either this way or this way, and this will have a series of atoms that are actually called the C stacking, sorry, A stacking again, right. So I take a cube, right. So the way they would have taught what is a cubic close packed structure versus what is a hexagonal close packed structure is the way to visualize it is I will visualize it along the 1 1 1 direction or along the C axis, and then I say if I have an AB stacking, then I am going to, and then this repeats, then I am going to say that this is a hexagonal structure, or the packing is hexagonal close packed, whereas if I have ABC, then that actually it's funny because that introduces more symmetry elements, more 3-fold axis of symmetry, right. So that gives me, this will be a 3-fold axis of symmetry, here this will be a 6-3 axis of symmetry, okay. This is 3-bar axis of symmetry, in fact 3-bar means there is a 3-fold axis of symmetry, right. And so this will become a cubic material, right. So this so if you pack atoms in this fashion in a very closed so that I leave as little voids as possible, that is called a cubic close pack. But so the difference is in stacking, right. So that's how we were taught, right. So in other courses, right, AB versus ABC. But here you can come from symmetry and then say this has a 6-3 symmetry. So the only way this can have 6-3 symmetry is if it has AB stacking. So AB stacking is a consequence of this having a 6-3 symmetry, right. Whereas the other one has a 3-bar symmetry, and the only way this can have a 3-bar symmetry and M 3-bar M symmetry is if it has in a face centered face centered cubic lattice, is if it has a ABC ABC sort of symmetry, sort of stacking. So, the stacking sort of follows from the symmetry and the structure, right. So it's not something fundamental, right, but this is easy to visualize. If I say it has AB, ABC, ABC, then I see that, oh, these structures are after all somehow sisters of each other, they are not that different, right. So it is just that so if I remove a C plane here, right, so I put vacancies of if I have platinum, or if I have any FCC metal, right. So I have ABC, and this is so this is platinum, this is platinum, this is platinum atoms, this is platinum. I put some vacancies of platinum and just condense this. That means I make bonds between these two planes. Then it locally becomes a hexagonal structure, right. So HCP close packing with a hexagonal structure. Okay. So so it's so or you can twin these materials, or you can do a lot of things. Okay. So anyway, so these are sort of close enough to each other that so many metals either are packing in a if they're closely packing, they are packing mostly in a CCP or an HCP configuration, right. So these are more popular among metallurgists. Okay. So with that, let us end the discussion on visualization of structures for now. And we take up so far. So we have seen so just to summarize, we have seen what is to start with, what are the 7 different crystal systems, right. So in the discussion on our structure and how they come from underlying symmetry operations, we have seen what are Bravais lattices, what is the use of defining Bravais lattices so as to not lose out an eye on the symmetry, on the underlying symmetry when you are actually looking at a unit cell, right. So that is the purpose of defining a Bravais lattice. Then we have seen point groups actually, and then we said there is something called underlying point groups that are important. So we have to actually understand how point group of point symmetry operations act about a certain point or certain axis, and so then we and there are 32 of them. We have developed them based on different crystal systems, 7 different crystal systems, and then we said, okay, so point groups then lead to a bigger idea of space group inside a crystal, right. If I need a template of so if I place an atom and I say so I need a template to place these atoms in a periodic fashion, then I need to know its space group, and I need to know so space group will say something so it has all the details about what is the position, what are the symmetry positions, what are the point group symmetries that several point group symmetries that exist, what are the different points about which there are these point group symmetries, right. That along with information about the lattice parameters, the unit cell parameters should give me the template, the complete geometric template of how the unit cell will look like, right. Then using X-ray diffraction or something like that, so then I will tell you where to place my motif, right. So what is that unique, what is that one position where I can place my motif, and then this template will completely repeat everything, repeat my motif, right. So based on so what I refine using X-ray diffraction, right. So then I have a motif, I have the template which is the complete lattice, and so looked at with the eye of symmetry, right. So I have the complete crystal structure, right. So just by understanding the symmetries, I can sort of understand where all to put the atomic positions and things like that, right. So then we started visualizing certain standard things, such as what is a diamond cubic structure, where is the diamond glide coming there, that gives it a tetragonal so a tetrahedral silicon so the diamond glide gives so make silicon also sit in the center of the tetrahedron, right. So in the diamond cubic structure, and then we said so this has a greater symmetry than what the structure, what every point has, what every so then all the points put together, right. So the entire structure together conspires to have a greater underlying point group symmetry. And then we moved on, we looked at zinc blends, we looked at woodsides, right. So the other tetrahedral like configurations, right, so of atoms which are connected to each other. Then we also looked at perovskites earlier, where we have an octahedral connection, right, so of oxygen atoms, let us say, And then finally we ended by visualizing metals, right. So, which are the CCP sort of metals and the HCP sort of metals, right. And in between we sprinkled with a bit of what is the big deal about this. For example, when looking at Woodsides, we introduced the idea of what are called HEMTs, right. So, high electron mobility transistors, and so wherever possible, we sort of put in the bigger picture as to why we are studying this. Okay. Now, so that summarizes whatever we have done from the structure point of view, right. Now, structure and symmetry point of view. Now, why did we do all these things, right? So we did all these things so that we will be able to say something general about the properties, right? Now, what is that? How can I say that, right? So I can say that using what is called again Neumann's principle, which states that any property which is a tensor follows at least the symmetry of the underlying point group of a crystal. By the way, before moving on to what this statement means, if I give you an amorphous material, a glassy material, right? A glassy material, doesn't have, a direction dependence or anything like that, right? So, a glass or an amorphous material in this course or in general, it's a good approximation to, this will be the most symmetric material ever, right? So this will have an n-fold rotation where, 360-degree rotation symmetry, right. So wherever I go, the environment is going to be similar, right. So because I do not have a particular lattice and structure for this, right. So I'll model glasses or liquids as really very highly symmetric materials, right. So I don't so I'm going to break the rules of translation symmetry because they don't have an underlying lattice, let's say, right. So there is no periodicity, at least long range periodicity. Break the underlying translational symmetry constraints, right. So in general, right, so I mean, of course there are different types of glasses and so it's a big field by itself, but in general if I say in this course that I have glass, right, so you can assume that glasses are what are called isotropic, which means they have same properties in all directions, or in general I have a 360, a 2 pi rotation symmetry, a 360-degree rotation symmetry about every axis. Okay. So any portion of glass is equivalent to any other portion of glass, however I see it, right. So all sorts of symmetries are there in glass as much as you can think. Okay. So if I am disordering a material, right. So this goes sort of counterintuitive. Disordering a material means I am increasing its symmetry, right. From a crystal, if I am making a glass, right. So how do I make a glass out of crystal? So how do I what is any glass making process? I take a crystal, I heat it, I melt it into the liquid phase, right. Liquid phase is sort of disordered, there is no order or there is no structure to the liquid phase, long range order is what I mean, right. So and then I suddenly quench it. When I suddenly quench it, the liquid phase becomes solid, but the structure does not have time to reorganize into a crystal, right. So the structure of the liquid will sort of be frozen into your glass, right. So that is the way to make a glass, right, that is glass making. So glass is a disordered solid, right. So the structure, I do not have a unique periodic structure that I can define, very simply put, right. So you still have what is called medium range order in a glass and various types of glasses, etc. But very simply put, there is no long range order in a glass as there is in a crystal, right. But by disordering a material, I am actually increasing its symmetry. Okay. So that's the big deal about glass. Okay. So, now let us come back to the Neumann's principle. Now, what does it mean that so I have any property which is a tensor. Now, this property should at least show the underlying symmetry should dictate what components of this tensor exist. Underlying point group symmetry. Did I write point group here? Underlying point group symmetry, right. So, that is the most important thing. So, underlying point group symmetry dictates what P my property should be. Okay. Now, it becomes easy if I start solving some problems and explain you with examples rather than making vague statements such as what I just did. Okay. So, let us take the example. I mean, so we actually, if you remember, just before starting symmetry, right. So, I was actually talking about inversion symmetry, and I said if I take a first rank tensor or a third rank tensor or a fifth rank tensor, let us call it F I J K L M, or odd rank tensors, all these tensors do not exist, right. So, they all go to 0 if material has a 1 bar symmetry. Right. This we have shown, right. So, we looked at Dijk and we said okay. So, Dijk would exactly transform like so a tensor which is xi, xj, xk, right. Now, so if I have 1 bar symmetry, right. So, x1 will transform to minus x1 under 1 bar operation, x1 will transform to minus x1, x2 will transform to minus x2, x3 will transform to minus x3. But 1 bar symmetry means the tensor, the property tensor, right, tensor meaning property tensor obtained after inversion, after 1 bar operation, should exactly be the same. This is the definition of symmetry, right. That we started with. Okay. So, if I have a property Dijk, right, and then so I invert my so I say that there is a 1 bar symmetry, that means so Dijk will transform like xi, xj, xk, right. So, xi, xj, xk under 1 bar will transform to minus xi, minus xj, minus xk, which is nothing but minus xi, xj, xk, right. So, Dijk will transform under a 1 bar operation to minus Dijk, right. So, if I invert my axis and I look at it, that is a 1 bar operation, right. So, then whatever I am measuring in my previous axis, now my axis is inverted, my frame of reference has inverted. So, what I measure will be a negative of the property that I have measured earlier. That is the way to interpret this, right. So, earlier my axes were 1, 2, 3. I measure Dijk, right. Now, my axes are new axis are minus 1, minus 2, minus 3, but still if I have 1 bar symmetry. So, here I measure, I should measure ideally minus Dijk. Okay. Now, okay, so these are right handed system, this is left handed system, all that is correct, but so in the new axis I should measure ideally minus Dijk. Okay. However, symmetry means just like so I rotated the axis earlier, right. So, I said there is 3 fold axis of symmetry and I rotated the axis and nothing changed in your Vesta picture, if you remember, right. Symmetry means nothing should change. upon a 1 bar operation. As a result, I should have dijk equal to minus dijk, and so the only way this is equal is if both of them are equal to 0. As a result, I cannot have any tensorial component of piezoelectric tensor, right. Similarly, I cannot have any tensorial component of pyroelectric tensor. Similarly, I cannot have any tensorial component of a 5th rank tensor, right, or this is a second harmonic generation tensor, right. So, any 3rd rank tensor, any 1st rank tensor goes to 0, right. So, this sort of gives us an idea of what the symmetry property correlation means. I do not really need to know what the property is. So far, I do not need to know that dijk is a piezoelectric tensor. Dijk can, for all you care about, it can be second harmonic generation, it can be something else, right. It can be some magnetic it can be so some sort of an elastic tensor, right. So, 3rd rank elastic tensor, I do not even know what it is, but let us say it is, okay. I do not care what it is, I do not care about the physics of it. All I see is if the material has a 1 bar symmetry, then if this is a 3rd rank tensor, it can be whatever property, it can have all these nice origins, atomistic origins of that property, I do not care, that should not exist in this material. That is what symmetry imposes, right. So, this is the Neumann's principle. Underlying symmetry is if I have a 1 bar as the underlying symmetry, the dijk should at least have the 1 bar symmetry, which means that it should not exist, okay. Okay. Now, what about so let us go to 2nd rank tensors. Okay. For sake of argument, let us call it epsilon ij, epsilon for dielectric constant. But it does not matter, I can talk about sigma ij, I can talk sigma is the conductivity, I can talk about nij, where n is the refractive index. It does not matter which property I am looking at, right. I cannot talk about, by the way, I will not be talking about I forgot the notation that I have used for stress. I think this is strain and this is stress, right. So, strain and stress are not property tensors, these are what are called field tensors, right. So, these are not properties, right. So, these are just they happen to be tensors and they are field tensors, right. So, what I am looking at are what are called matter tensors, right. So, this thing we have defined earlier. So, matter tensors are property tensors, right. So, it does not matter which property I am looking at, I can look at susceptibility, magnetic susceptibility, whatever, does not matter. As long as it is a 2nd rank tensor, the symmetry operations that I am going to operate work on all these tensors, okay. Now, any 2nd rank tensor, let us take the example of epsilon ij. Should under will transform as multiplication of 2 vectors xi xj, this we have seen earlier, right. So, the way this transforms, is one and the same, okay. So, now let us look at the inversion operation. Now, I have a tensor epsilon 1 1, epsilon 2 2, epsilon 3 3, epsilon 1 2, epsilon 1 3. I am going to write this as symmetric tensor. And the reason why this tensor is symmetric right. So, this component is equal to this component, this component is equal to this component, epsilon 2 1 equal to epsilon 1 2, right. So, this does not come from material symmetry, this rather comes from thermodynamics, right, in case of what are called conservative properties. So, this we will prove this later. But for now you can imagine that all 2nd rank tensors by virtue of accept that, I am going to say accept for now, virtue of thermodynamics and or kinetics, or let us say so this is for all the equilibrium properties and this is for all the dissipative properties, right. So these are dissipative properties and these are conservative properties. So this is going to be our next module, but are symmetric. Okay, so we are going to agree to this fact for now, right. So I'm not going to question why epsilon 2 1 should be equal to epsilon 1 2 until I come to that discussion in thermodynamics. Okay, so we will prove this later. Okay, so we will actually prove this later, right. Okay, so for now just take that fact. So I have this tensor which is supposed to have 6 elements. Okay, so and then I say that I have one bar symmetry, inversion symmetry, inversion exists, right. So epsilon 1 1, so xi xj will transform as minus xi minus xj, right. So that is xi xj, right. So it is not going to transform anything different, right. So epsilon 1 1 should transform as epsilon 1 1, and by symmetry that means that epsilon 1 1 equal to epsilon 1 1, but that is trivial. Okay. So inversion symmetry is so in the same vein epsilon ij should just transform as epsilon ij, and symmetry is not adding any extra constraints, right. So it is just saying epsilon ij equal to epsilon ij, that is what symmetry is saying, is not adding any extra constraints. So for a triclinic system which I have P1 or P1 bar, my epsilon or as any second rank tensor will have epsilon 1 1, epsilon 1 2, epsilon 1 3, epsilon 1 2, epsilon 2 2, epsilon 2 3, epsilon 1 3, epsilon 2 3, epsilon 3 3, right. So all the 6 elements will exist. Okay. Inversion symmetry does not play a role for second rank and fourth rank and so all these other rank tensors. Okay. So inversion symmetry is sort of useless, it is not imposing any additional constraints on my properties. Okay. Now let us change the game, right. So inversion symmetry is fine, we have dwelled on it enough so far, right. Let us go to a two-fold symmetry. Right, two-fold symmetry about 0 0 1, right. Now two-fold symmetry about 0 0 1, what does it do? So it is going to so my so the matrix that I have Aij is actually equal to minus 1 minus 1, sorry. So it is going to take something here to here, yes. So xy change, but z will not change. So that is 0 0 0 0 0 0, right. So our x1 goes to minus x1, x2 will go to minus x2 and x3 will go to x3. Okay. All right. So now I am going to look at each of these epsilon 1 3, epsilon 2 1 epsilon 2 2, epsilon 2 3, epsilon 3 3. I am going to look at each of these 6 elements and then see how two-fold symmetry is going to add additional constraints on each of these elements. This is my property tensor. Okay. Epsilon 1 1 is going to transform as x1 times x1, that is just epsilon 1 1, right. So no additional constraint here, nothing. Epsilon 1 2 is going to transform as again x1 x2, right. X1 x2 has again it transforms as epsilon 1 2, nothing. Epsilon 1 3 is going to transform as, now we are talking, right. So this is going to transform as x1 x3, right. So, x1 will go to minus x1, x3 will remain as x3. So, x1 x3 is going to transform as minus x1 x3. So, this is going to transform as minus epsilon 1 3, and by symmetry epsilon 1 3 should be equal to minus epsilon 1 3. So, that should be equal to 0. Now I am talking, right. Epsilon 2 2, epsilon 2 2 is, nothing is going to happen to it. So, that will be epsilon 2 2. Epsilon 2 3, if I have a 3 here, right. So, that is going to transform as minus epsilon 2 3 again, and so epsilon 2 3 equal to minus epsilon 2 3 by symmetry, and that is equal to 0. Epsilon 3 3, nothing is going to happen. Okay. So, just by having a two-fold symmetry, I have gone into a monoclinic system. My epsilon tensor, or any second rank tensor for that matter, has epsilon 1 1, epsilon 2 2, epsilon 3 3, all right. Epsilon 1 2 is okay, but all these other elements have become zeros. Epsilon 1 3s and epsilon 2 3s have become zeros, right. So, I have reduced, so 6 elements into just 4 elements. Okay. Having said that, you remember our discussion. So, if I have sigma instead of epsilon, right, sigma is the conductivity. Conductivity is also a symmetric tensor, and conductivity also has, sigma 1 1, sigma 1 2 0, sigma 1 2, sigma 2 2 0 0 0, sigma 3 3, right. So, two-fold symmetry, or you can also do the same, mirror also acts similarly. Will have a similar effect. Okay. Okay. So, here you go, right. So, I go back to my conductivity matrix, which is, sorry, conductivity tensor, which is sigma 1 1, sigma 2 2, sigma 3 3, 0, sorry, sigma 1 2, sigma 1 2, 0 0 0 0. All right. So, I am back again to the discussion that I did when I was having Hall, when I was discussing Hall conduction. So, I have some transverse conductivity here. Which is non-zero, right. In Hall effect, I said we have to always look for those less symmetric materials that could have sigma 1 2, which is non-zero. This is like the Hall, so this is Hall conduct, or sorry, so we talk in terms of resistance, right. So, rho 1 1, rho 1 2, rho 1 2, rho 2 2, 0 0 0 0, rho 3 3, right. Rho 1 2 is or transverse resistance. So, this is the Hall resistance, Hall like resistance I must say, measured at 0 field, magnetic field, right. So, this comment we made, and we said that you have to be careful about such materials. Now, what are these materials? All the materials with a P2 symmetry, right, can have transverse, or less than P2, even P1, P1 bar, or PM, right, or I can have both mirror and so P2 by M, right. So, all these things will have sigma 1 2, okay. And so PM or P2 by M, right. So, all these are actually monoclinic or triclinic systems. So, if I am actually doing Hall measurements on materials that are monoclinic or triclinic, I have to be very careful. I have to understand that from material symmetry, there is already a component of rho 1 2 that exists, even if I do not have any magnetic field, right. So, even at 0 magnetic field, I already have rho 1 2 that exists, right. So, I have to take that into account, and I have to ramp up the magnetic field, and then look at the Hall conductivity, Hall resistance as a function of magnetic field. it does not pass through 0, right. So, this we have done earlier in one of the earlier so in the first few classes. Okay. So, one of the important materials that gallium oxide, this is called beta gallium oxide, again another wide band gap semiconductor like gallium nitride. This crystallizes in if I am right P21 by C sort of a phase, right. So, sort of symmetry. So, the underlying symmetry here 2 by m. This is a new, I mean, so there is a lot of research that is coming up on this material nowadays, right. So, gallium oxide is going to be the next big thing in terms of wide band gap semiconductors, right. So, a lot of people are trying to do research in this material now. However, if you are working on gallium oxide, beta gallium oxide especially, and you are doing a Hall measurement, the thing is be careful. Okay. So, you already have conductivity or you already have Hall resistance at 0, you already have resistance at transverse resistance at 0 magnetic field. It is not Hall resistance, but you already have some non-zero resistance at 0 magnetic field. Okay. So, that needs to be considered, and then you have to do a proper Hall measurement. Okay. So, so just otherwise that will yield nonsensical results. Okay. So, all right. So, then so before coming to the next class probably what you can look at is what will happen if I have two-fold axis of symmetry, or 2 will of course lead to 3, right. So, to a second rank tensor. So, this we have seen, right. So, we go from monoclinic to orthorhombic system. So, I mean I can actually take a simple guess, right. So, I have only so epsilon 1 2 epsilon 1 2 0 0 0 0. So, I have only epsilon 1 2s which are remaining, right. So, my so if I have two-fold axis about the C axis about 0 0 1, right. So, the only cross components that are remaining are epsilon 1 2s, right. Now, if I also have two-fold about 1 0 0, then epsilon 1 2 also goes to 0, right. So, that is going to be a simple guess, but I am going to have my epsilon or any second rank tensor without any transverse components, right. So, no transverse components. Okay. So, I first apply, so the way you can do it is I first apply two-fold axis about 0 0 1, come to this matrix, I have come to this tensor, and on this tensor I apply two-fold about 1 0 0. So, the only components that will become 0 are epsilon 1 2s. Okay. So, that you will yield this tensor. Okay. So, no transverse components, only direct components. So, as a result so you do not need to worry about so Hall measurements from orthorhombic system and up is okay, right. So I mean okay meaning there will be other artifacts that will come up if you are not ramping up the magnetic field, but you will not have a transverse resistance that is coming because by virtue of the crystal structure, right. So, orthorhombic and up, in symmetry there is going to be no transverse resistance, which is the rho 1 2s, rho 2 3s etc., right, or that there are rho 1 3, right, that comes by virtue of symmetry. Or more accurately, symmetry actually kills by virtue of less symmetry, right, or symmetry kills all transverse components. Okay. All right. So, with that let us conclude this lecture. So, we were trying to look at symmetry property correlations, and just I do not care what the property is for now. I am just going to say if the underlying symmetry is this, the property should follow that at least should have that much of underlying symmetry. And what do I mean by that? I took examples of 1 bar symmetry. I said if there is 1 bar symmetry, there is going to be no piezoelectric coefficients, but if there is 1 bar symmetry does nothing to a second rank tensor, right, irrespective of what the second rank tensor is. Twofold axis. Twofold axis, you know, so we started with second rank tensor, we will go to third rank tensor in the next class. So twofold axis is just going to kill off my certain transverse components, right. So about, you know, so the 1 3s and the 2 3s, right. Whereas if I have two twofold axis, the third twofold comes for free, right. So in a so I am moving from monoclinic to orthorhombic system, and there that kills off all the transverse components of a second rank tensor, right. So now I have to just worry about 3 components in an orthorhombic system, right. So 3 components of epsilon, 3 components of refractive index, 3 components of you know, resistance, or whatever be the second rank tensor. Okay. So so yeah, so we'll keep on increasing the symmetry in the next class, and then, you know, go towards higher rank tensors 2, 3, 4, right. We will do some calculations, and then, you know, and, you know, conclude this part of the course. Okay. Thank you.